sodium chloride, barium nitrate, forms barium chloride and sodium nitrate. Yeah, is that balanced? No. So we have to put a 2 here, 2 over here. That takes care of it. What is that kind of a reaction?
Double replacement.
It's a double replacement. So 2 ionic compounds and they switch partners. And remember with those that you've got to rebuild the compounds based on the charges. You can't just take the Na and put it with NO3 because that wouldn't balance the charge properly. A lot of these things, a lot of the issues with these kinds of problems I've noticed in the classes is not so much that you don't get balancing equations or any of that kind of stuff. It goes back to the chapter about naming compounds and writing compounds from names. So if that's still an issue for you, please work on that before the exam on Tuesday, because that will be another big part of the exam. All right, and then the next one, magnesium, which is Mg, reacts with hydrochloric acid, which is HCl, to produce hydrogen gas and another product. What's the other product? Yeah.
MgCl2.
Right, so it's a single replacement, because on the left side, the magnesium is by itself, on the right side, the hydrogen is by itself. So that means the other 2 things need to come together, the other 2 things being Mg and Cl. It can't just be MgCl, because Mg is a +2 ion, Cl is a -1 ion, so there's got to be 2 Cls. So that means this isn't balanced, but we can balance it by putting a 2 there. Good so far? All right, stop me if you want to talk more about these things. Okay, this one, the equation's given for you. How many grams of sodium oxide are produced from 57.5 grams of sodium? So this is that typical type of problem. 57.5 grams of sodium. And then we've got grams of sodium to moles of sodium. Moles of sodium to moles of sodium oxide. And then finally, moles of sodium oxide to grams of sodium oxide. Okay, then we just got to fill in our numbers. We get the middle part from the equation, 2 of these to 4 of these. And then the others are the molar masses. So sodium is 23 grams per mole. Sodium oxide, we have 46 plus 35 is 81.5. And then we can calculate that. .5 divided by 20.
Isn't your Na2O wrong?
Yeah.
Is it?
Yeah, I think it's like 64.
Let me say that again. Oh yeah, because it's Na2, right? So 23 and 23.
Plus 16.
Plus 16, thank you. So 23 and 23 is, I was doing Na2Cl for some reason, I don't know why. 23 and 23 is 46, and then plus 16 is 62, right? 62. Okay, thank you. 57.5 divided by 23 times 2 divided by 4 times 62. 77.5 grams of Na2O. Yeah, so make sure you can do those kinds of problems. That'll for sure show up on the exam. And then second, is this a redox reaction? What do you think? Got some head nods. Yeah, how do you know?
Because the NA is alone.
Yeah, because the Na and the oxygen actually are alone on the left. And so if they then become a compound, you know there has to be some change with the electrons. So we can look at the charges. Na in this reaction goes from 0 to +1. O goes from 0 to -2. That first one going from 0 to -1, is that a loss or a gain of electrons? Loss, because it's getting more positive. So that's loss of electrons. And then O going from 0 to -2 is reduction. Okay. And then when 3.5 moles of acetylene gas undergo combustion, which is what happened in the pumpkins out there, that's what we'll be doing on next week. You create acetylene by reacting calcium carbide with water. And so they would, I don't know if you saw that part, but they had a little thing in the pumpkin with the calcium carbide, poured some water in, closed it up to let it react. It fills the pumpkin with acetylene gas, and then it combusts when you light it. Hopefully, it's supposed to anyway. So combustion, we know, is reaction with oxygen. And what are the products of combustion?
CO2 and H2O.
Yeah, CO2 and H2O always. So we can write that equation. It is not balanced. To balance it, we're going to go 2, 4, 2, and 5. All right, yeah. So then we know 3.5 moles of acetylene. And we want to know how much oxygen. So that means we want the ratio between the moles of acetylene and the moles of oxygen. Okay. 8.75 moles of oxygen needed to react. Okay. Any questions about that? All right, let's move on. So last time we talked about solutions, we talked about what makes a solution, and we talked about how to calculate concentrations. You got a little bit of practice of that in lab on Tuesday. I was thinking about this. We should have one more quiz on solutions. I don't really want to do it Tuesday because it's right before the exam. That seems weird. But maybe we should do it Thursday next week, so that even though it's after the exam, the material is on the exam, at least we'll get a chance to do one more quiz. And the lab still isn't due until the next Tuesday, so that might be a good time to do that. So let's do a quiz on the solution stuff next week, a week from today. Okay, today we're going to talk about the last part of the solutions chapter, which is some other solution-like compounds and how they behave. Suspensions and colloids. Suspensions and colloids are characterized by having larger particles than solutions. So recall from last time that a solution, well, here we can put it back up there. In a solution, like sodium chloride solution, you have the solute broken down to the molecular or atomic level, where it's split up and surrounded by these water molecules. In suspensions and colloids, that's not the case. Suspensions and colloids have larger particles. In suspensions and colloids, the particles are so large that the water molecules can't totally surround them and bring them into solution. And so they're characterized by light not getting through as well. Because it bounces off those particles. So as you saw in the solutions on Tuesday, when you make a solution of something, like when that potassium nitrate went into solution, you could see totally through it. It just looked like clear water. And if you shined a light through it, or a laser or something, it would just go right through. A suspension or a colloid is something that kind of has a cloudiness to it. So that if you try to shine light through it, some of the light gets through, but some of it gets diffracted as well. So think about things like milk, for instance, or I don't know, other things that look like that. But I'm drawing a blank. So you have another good example.
Orange juice.
Orange juice, sure. It's a suspension. Medications, pretty much anything you have to shake. Like if there's anything that says shake well before using, that's an indication that some of this stuff is going on. And in fact, that's what separates suspensions from colloids. Suspensions the particles are big enough that they will settle over time. So if you let something sit and particles settle down to the bottom, that indicates that that's a suspension. So anything that says shake well, like orange juice with pulp in it, is a suspension. The pulp is suspended in the orange juice. Probably some of the other stuff too, because you can even if it's pulp-free orange juice, you still have to shake it, right? Usually, I think so. If you just try to pour it off, it's kind of watery. Yeah, I think it's a suspension. And then colloids, you still have that kind of cloudiness, but the particles don't settle. So the particles are so small that they are held basically by the water. They're not in solution, but there's not enough gravity on them to actually get them to settle out. And so something like milk is an example here. Milk, as you get it out of the cow, it was a suspension and will separate, but milk in the store does not. You have to shake milk. It's not like the stuff goes to the bottom. Anybody know why that is? That process is called? It's called homogenization. Homogenized milk, is like you'll see on it, it means homogenized. All that means it's been shaken so hard that it breaks all the particles up into small enough pieces that they stay in solution and they don't separate. So if you shake something hard enough, sometimes you can form enough of a stable suspension that it won't settle. All right, so how do you get rid of these things? Or how do you separate these things, I guess we should say. The book has a nice picture of this, so we'll steal that. Oh, here, I saw this too. The book has some examples of these different ones. Types of colloids. Hairsprays, clouds, fog is a colloid. The solid and the liquid part, paints, gelatin, blood plasma, things like that. So you can take a look at that. If I were a good teacher, I would have prepared ahead of time and need that stuff, but sorry. All right, so here are the different types of particles. We've got particles in solution, particles that are colloidal, and particles suspended, so suspension particles. The orange circle is the solution, the green triangle is the colloid, and the red square is the suspension. So you can see on the one on the left, over time, the suspension particles will settle out, but the others will stay. Okay. The solution particles you would never see, just it would clear up. It could change color, but you wouldn't see it. You wouldn't see the individual particles. The colloid, it would still look probably cloudy. Then in B, you could filter this stuff out. So you could pass the stuff through a filter, and you're going to try that. You're going to do this next week, not next week, in 2 weeks in the lab. You can filter out those suspended particles, but again, the colloidal and solution particles do not get filtered out. You might get a little bit of the colloidal particles, which is shown here. But most of them are going to go right through the filter paper because those particles are so small. If you try to filter milk, it doesn't really clear up. It still looks like milk when it goes through that filter paper. So the way you get rid of the colloidal particles, you use something called a semi-permeable membrane. A semi-permeable membrane is just a material that has really, really small holes inside, like on the molecular level, and can only let things of a certain size pass through. It sounds fancy, but we see these kinds of things all the time. Something like plastic wrap, like that you cover your food with, is a semi-permeable membrane. So that will let small molecules through without allowing large things to pass. And then, importantly, a lot of the cells in our body are protected by semi-permeable membranes. And so we could talk about, and we will talk about diffusion through those membranes and what the consequences are for that. All right, so the semi-permeable membrane has holes that are small enough that the colloids cannot get through. So in this picture, it's a little bit of a weird picture, but this picture, the arrows are showing that the solution particles can get through that bag, but the suspension and the colloid particles are stuck inside. And we're going to do this in lab in a couple weeks too. I know some of you probably done this already in biology. Yeah. So I know they do that too, but we're going to do it also. So you'll just be the experts. You can show everybody what to do. So that's the difference between those things. All right, so let's talk a little bit about these semi-permeable membranes. There are two important processes that happen across semi-permeable membranes: osmosis and dialysis. Osmosis is the movement of water across this membrane. Dialysis is the movement of particles across this membrane. Once again, I will take a nice picture from the book. So let's say we have a container that we separate in the middle with one of these semi-permeable membranes. On one side, we put pure water. On one side, we put sucrose, table sugar. The water will diffuse back and forth through that membrane, and that's called osmosis. But importantly, it will go more in one direction than the other. The water will more go toward the high area of high solute concentration, which is sometimes defined as lower water concentration. But basically, the way I like to think of it is it tries to equal out the concentration. So wherever the water has to move to make the concentrations equal, that's what's going to happen. In this case, you've got a concentration of 0 on the left and a concentration of something greater than 0 on the right. So the water moves from left to right. And the neat thing about that, or one of the neat things about that, is it actually pushes the level up over time. So the osmosis, that force of that concentration gradient, is actually doing work. It's pushing something. It's creating a pressure. And that pressure is called osmotic pressure. So the force of that water pushing in that direction is known as osmotic pressure. And the tricky thing about this is thinking about concentration versus osmotic pressure, because it's opposite. The area of lower concentration, of lower solute concentration, is the one that's exerting the osmotic pressure. So it's going, from, in this example, from left to right, not from right to left. So low concentration exerts the higher pressure. I guess I should write that down here. Lower solute concentration exerts higher pressure. Okay. And so that can cause problems for things like biological systems. Our cells are protected by these semi-permeable membranes, but if water gets forced in or if water pushes outward, you can destroy the cells. So we talk about those three different situations compared to the pressure, or compared to the concentration. So let's take a look at this. There's a here. Like that. So we've got three possibilities of a solution. So if you think about a blood cell placed in solution, That's really the same thing as what we saw in the last figure with that membrane separating it. But the membrane in this case is the cell membrane, the thing that goes around the cell. And so in the first example, you have what we call an isotonic solution. Isotonic solution has the same solute concentration as what's inside the cell. So water can go back and forth and diffuses through that membrane, but it doesn't go more in one direction than the other. An isotonic solution can be described in a few different ways. It is a 0.9% M over V sodium chloride solution. So 0.9% mass by volume. Or a 5%, also M over V, glucose solution. Different concentrations because of the different number of particles that would be dissolved in those. The molarity ends up being the same. Well, the molarity of ions in NaCl, the molarity of glucose is about 0.3 molar. That's the same as what you have inside the cell. So that doesn't force anything in or out. So a hypotonic solution then is something with a lower concentration. We should say. So less than 0.3 molar. And a hypertonic solution has a greater concentration. And let's think about what happens to those blood cells when they're experiencing those concentration gradients. When there's a lower concentration, which way is the water forced? If the blue solution has a lower concentration, which way does the water go?
Into the cell.
Into the cell. You see that? Lower concentration, the water goes from lower concentration to higher concentration. So it pushes into the cell. Right? And that's called hemolysis because eventually what will happen is it will cause the cell to burst. In the other example, you use a hypertonic solution, meaning you have greater concentration on the outside, and this causes water to come out of the cell, out and into the other solution. And if that ends up going on for long enough, you get a situation called crenation, which the cell is basically shriveling up. It's losing its water as the water goes out to the outside where there's areas of higher concentration. So if this happens in our body, that's usually a bad thing. There are some situations where an emergency doctor or something might induce one of these states on purpose. Like if you have to really, really quickly increase blood volume, you can put a hypertonic solution in your blood and kind of suck liquid out of the blood cells to increase the blood volume, like in an emergency situation. But again, it's kind of dangerous because you kill a lot of cells that way. So have to be careful about that. The other thing this is used for is we'll just have like food. Have you ever made pickles, like pickled things? No, some people, yeah. So one of the things you do, what kind of pickles do you make?
For like Thanksgiving, we always do like pickled like beets and stuff.
Okay. So do you remember how it works? How you do it?
You know, you kind of just like soak it in vinegar and then kind of just enlarges it.
Okay. So that, yeah, I haven't done beets, but I've done like cucumbers and radishes and stuff like that, pineapple. But one of the things you do first is you just throw a bunch of salt and sugar in with the stuff that you're pickling, and then you just let it sit for like 10 minutes. You should try this. You can try it when you get home today. Just take some old vegetables and throw some salt in with them and like shake it up in a little jar. And after about 10 minutes or so, there will be a pretty significant amount of liquid on the bottom of that container. Even though you didn't put any liquid in there, what's happening is you're creating this area of super high concentration on the surface of the vegetable, and the plant cells are then giving up their water through that last process, pushing the water out into the area of higher concentration. And so after a while, you see like water starting to fill up on the bottom, not a lot, but there's water in there, and you pour it off, and then you put in the vinegar or whatever to kind of push back those flavors back into the foods. So yeah, hope I didn't make anybody too hungry. But that's what I do. So that's so the hard thing about this, I think, is keeping all this stuff straight. Like what solution causes what condition, because it kind of goes back and forth. If you have a higher concentration, that means the water is getting pulled out. And the way I always keep it straight is with this. Just thinking always about equilibrium, making things equal. The water is trying to move to make everything equal. So that's really what we're going for, that eventually we want all the concentration across both ways to be equal. The other thing that happens with semipermeable membranes is these small solution particles can go through them. And that's called dialysis. And that's something that we'll be looking at in lab in a couple weeks either. But have you heard of like kidney dialysis? So what's happening there and what your kidneys do is they use this idea to allow things that shouldn't be in your blood, toxins and stuff, to penetrate through a semipermeable membrane to an area where those aren't there. So that's how a dialysis machine works as well. You take your blood out, pass it through this machine. This machine has these membranes, and there's a solution on the other side of the membrane that the stuff can diffuse into. And of course, that solution has to be kept carefully balanced with your body's concentration, because otherwise all the stuff that's supposed to be in your blood is also going to, if you just use water, all the stuff in your blood is going to diffuse out and dialyze out into the water. So it has to be carefully balanced so that only the stuff you don't want in there anymore comes out.
Is there like a chemical reason why dialysis makes patients so tired?
That I don't know.
It's like you get all the blood back.
Yep.
It's just clean.
Right.
I didn't know if there was like a particular chemical reason behind.
I don't either. Maybe. Yeah, maybe. Does anybody know? Do we have any?
I just know that like
Yeah.
that's like the number one thing with dialysis is that it like takes all the energy out and exhausts patients who just sit there for hours at a time. So I don't know if there was like a real reason behind. Yeah.
I don't know. Should we ask the internet? Here, why does dialysis make you tired? So the UK National Health Service says it's caused by the effects dialysis can have on the body. Well, that's not very helpful.
It's really no big deal. I was just curious if it was chemical.
Yeah, I'm curious too. It sounds like probably not.
Looks like it just says that your blood pressure goes down.
Yeah, your blood pressure goes down. That's certainly going to cause tiredness.
Because then you don't get oxygen where you need it.
Yeah. This might not be helpful either. I don't know. The main reasons of fatigue are loss of kidney functions and malnutrition due to dietary restrictions.
Oh, yeah,
And stress and worry and stuff like that. So yeah, probably not a chemical thing then, but probably something in there. Thanks for asking. Other questions about this? More stuff going on, more spooky stuff in the building. All right, well, that's it for this chapter and us today. So exam on Tuesday, please study. I will be around in my office tomorrow. So if you need help, you've got questions or whatever, come by or just send me messages. I'll be able to answer you all weekend too. Tuesday before class, or Tuesday in this class again, we'll be having kind of a last minute question